natural exclamation mark. That is a bar.
Yeah, so this is the for the full CFT, so the Moonshine module is only the title part, but if you like to describe a full CFT, you have to get the left and the right part. But it turned out that then for the computation of the entropy of the black hole, that's what you should do. And for, I mean, for the I don't really have a stance this, so because we didn't continue by trying to what we hope is a very classical limit by using a family of extreme values to evaluate when we don't know if they exist. Now, mathematically, this is not too hard to understand because of course, one has asymptotic formula for the coefficient of the J function, right? And that's why this pi factor comes in. But the thing is that maybe there is some more physical interpretation behind. Yeah, so this is what I can say about my understanding of not of 71, but at least of 47 times 59 times 71. So now let me come to the second theorem. So I have written it up here again, what Shellacon did show in 1992. And he showed that there are 71 possibilities for the F-Moody subvertex operator algebra, or self-full vertex operator algebra, 24. So one has a trivial F-Moody algebra, that's the Moonshine module. Also, we don't know if it's the only vertex operator algebra problem. So this is a long, open-standing problem, and I also cannot report any progress about this. Then, what could happen is, since the V1 part is a reductive V algebra, and it turns out it's either a billion, and in this case, we get the Heisenberg subvertex operator algebra, which is realized by Leach, that is vertex operator algebra, or that's what Shellacon shows. There are 69 other cases where the V1 is a semi-singly algebra, and then in this case, the subvertex operator algebra is always central charge. Now, the goals are to construct all vertex operator algebra in all cases, to show uniqueness in all cases, and now that's what I will concentrate on, to find a better description of this list which he constructed but which came out of a computer. And so here is my description of Shellacon's list, for which I use Niemeyer. So recall that there are 24 evenly modular lattices called Niemeyer lattices, and 23 of them have a non-trivial root sublattice of maximal rank 24. And then one can describe this Niemeyer lattice by looking at the so-called group code, which is the sub-group in the discriminant group of the lattice, which is maximal isotropic. And this approach was used by Bancroft to classify all the Niemeyer lattices. So in each case, for each root system, you have a unique such group code. Now, here's how you can use it for the F-Moody algebras. So what one has is that the 69 non-abelian F-Moody structures of self-full vertex operator algebra of central charge 24 are in a natural bijective correspondence with the equivalent class of cyclic subgroup set of positive pi of the group code of the 23 Niemeyer lattices. So what you have to do is you have to look at all the 23 group codes and look at the, essentially you have to look at the vectors up to equivalence. So for example, in the Oleg code, which occurs for one of the 23 Niemeyer lattices, we know that the automorphism group N24 is transitively on the objects in the dotted class, and so there's only one vector, so then it generates a cyclic subgroup of order 2.
What is positive?
Yeah, this I will explain. that when what I define as an orbit group lattice, that these are the cases, these positive types are exactly those cases where this orbit group lattice corresponds to a Lie algebra dimension larger than 4. And further, Charlton gave a little problem called D for the Finite algebra of V. This is the maximal extension of the Kasmudi subvertex algebra by single columns, and this one can also be described from the Niemeyer group in the cyclic set under the above cyclic correspondence. Okay, now let me explain a little more how this works. So this is a table who explains everything. So you have here this Niemeyer lattice, this blue code, and you take a cyclic subgroup generated by code vector Z. Now, the root lattice is a direct sum of certain component of ADE, those 3, and so you can also decompose the code vector accordingly. And so what one likes to define is what I call the orbit lattice of this Niemeyer lattice by this cyclic group, and here it's the way it's done. So I have to do this eventually for the individual components of the root lattice. So if this is the ADE component, and this is the element in the discriminant group of this lattice, then I assign to the orbit group lattice by this line here, and I also assign to each individual component this as the type. And
the type is just a symbol.
The type is a symbol, a formal symbol.
It's like a frame sheet.
Wait a second. This is a formal symbol. So now, I mean, you are already. So what I'm doing here is why I call this orbit. I mean, you know, so if you have the E6 diagram, E6, that's the E6 thinking diagram. You are able to extend it to the affine Dinkin diagram, and then so the blue code for E6 is the cyclic group of order 3, and now you can realize this as a diagram automorphism of the affine Dinkin diagram, and then you look at the quotient diagram, and that's essentially what's going on here. And so now the type here is you can realize this also by an automorphism in the Weyl group, and then this would be the frame shape of this element in the Weyl group. Okay, that's what we complement. Now we also need the level in this for intelligence here. So what we take is let L be the order of this generator of our cyclic group, and Ni be the order of the component Ci in the corresponding discriminant group, and then we first define the orbit root lattice as the direct sum of this orbit root lattice for the individual component, but we scale it by a certain factor Ki, and this are defined as follows. So we take the order of C divided by the order of Ci times alpha, where this normalization factor alpha is 1, if the norm of the cyclic subgroup is 4, and 2 if the norm of the cyclic subgroup is 6. Now, what is norm of the cyclic subgroup? So if we look at the vectors represented by the coset corresponding to this subgroup in the blue group, and if there is a norm, if 4 is the largest norm occurring, then alpha is 1, and if it's 6, then it's 2, and if it's larger, then it's undefined. Yeah.
The third line, S of 0 is R.
Yes.
What's S of 0?
Yes. So I didn't here put in so if it's a zero component of zero, then
Oh, S
I
of 0
just
is S in the vector. It's just an AD.
it's F. Yeah. Okay. And then I will give you in the next slide an example. And then this is the root sublattice, orbit root lattice, and then the whole orbit lattice itself is this orbit root lattice extended by the orbit group code, which is essentially just a component-wise projection of the element of the whole group code onto the group groups of the orbit root lattice. Okay, so this drives one correspondence. Now let's see how this works in real life. No, that was one. Yeah, so I have here 3 of the 23 Niemeyer lattices with root. So, here in this example, the group code is very simple. It just has order 2, so you generate this element. So if you take the 0 vector, of course, nothing happens, and you will get the Niemeyer lattice on also your new root orbital lattice is level 1. Here, for the non-trivial vector in the group code, you have to divide the 16 by this order 2 orbital, and you get B8, but by my rules, the level here on the second component comes 2. And I also have given here the type, which is the formal product of the type of the individual root components. And so you can do the same. Let's do the Golay code case. So you see, if you have an octave in the Golay code, what you will get is this corresponds then to because here 1 would give you A0, which is empty, so this root system we have to remove. So what you have is left A1 level, A1 to 6, and it turns out to be level 2 by the norm rule, and here we get A1 level 4, we have to multiply it by 2, because alpha is 2, and we have here minimal norm 6 for the Golay code. And so I also added here A3 to the 8, because you see it can sometimes happen that the type is not positive. It means that you have a negative exponent. In this case, you ignore. So it happens that the rank is either 24 or 0, but we ignore it. And in the other cases, you will see.
Why do you ignore?
Because they are not in Shelton's list, right? So I have no idea what they are for. But,
what is that? What was the address?
What?
A1 to the 8.
Yeah, so I don't know. So at the moment I'm ignoring them.
Not in group.
What?
Something not
Let me ignore them. Then the other what you see is this corresponds to a unique number in Shelton's list. Right? And so you get the whole Shelton's list, and you also get the clue codes if you take the input, and everything is correct. No mistakes, and I had to work also as long as it really matches this, but it's a perfect match. Now, let me organize the things a little different. So what happens is that there are 11 positive types occurring this way. There are 11 positive types, and now you can look at the rank of the corresponding orbit lattices. This depends only on the type. And then you can look at the discriminant rate of the orbit lattices, and it turns out that this also depends only on the type. So this means that these lattices all belong to the same genus. Right? And now I computed this magma. You can easily compute the class number for the genus. And now you can compare it with the number of vertex operators also you get here from Shelton's list. And you see there is mostly a perfect match, right? So you have a one-to-one correspondence between the lattices, the orbit lattices in this genus and the elements in Shelton's list, besides here for the cases D and J, where something needs to happen. What I also gave here is some composition factors for the full orthogonal group of the discriminant space which arise. Now, how can one understand this? Now, the following theorem is not.
Sorry.
Yeah.
Could you just go back to the very bottom?
Yeah. Okay. I added the 12th line because I didn't like to forget about the moonshine module, but it's somehow not really matches this. But I didn't like to forget it, so I added the 12th line. Now, why does it work? Now, one has the following general approach to classification of self-full vertex array algebras of any central chart, because they are in one-to-one correspondence to certain quadruplets consisting of a genus of positive definite lattices spanning K, an isommetry class of lattices in the genus, and an isomorphism class of vertex operator algebras W of central charge C minus K, such that the associated modular tensor category is isomorphic to the quadratic space modular tensor category, but here they have changed the sign of the quadratic form, and you like that one part is 0. And then the fourth information which you need is that you need an equivalence class of anti-isometries between the quadratic space of the lattice and the vertex operator algebra, and you take then the equivalence class under the cosat action, where you have the induced action of the orthogonal group of the lattice on the discriminant space, and you have the induced action of the automorphism group as permutation group on its modules. And now, why is this true? I mean, the one thing is we have to go both directions. So if you have the lattice in the vertex algebra, this has the same, essentially the same modular tensor category if you just glue them together, right? But for this gluing, you need here this identification, and it's also clear that when you have equivalent gluings under this double cosat action, then there's a corresponding vertex isomorphic. So this, I think, is a strict theorem in one direction. If you have this data, then you can construct a self-full relay. If you like to go the other direction, you need some more general conjectures about vertex algebra, but the idea is simple. You just take, in the vertex algebra V, you take the V1 part, and this defines the part, you take the Cartan subalgebra, and then you take the double commutant which defines the lattice. So you have naturally, up to conjugation, this lattice associated. You take the cosat, this is the W, and then takes a certain gluing, and again it's defined up to isomorphism when you look at this. So that's the idea. Now, if you like to apply this for central charge 24, so what we take is, yeah, we have already mentioned this, our element G is a French shape. In fact, it's a French shape of an element in the convex group. We know this from the dipole description of the Leech lattice. Yeah?
You don't get 25 over 1.
It's not positive. Okay. So you only get the positive one. So you get 11 elements in convoluted class of elements in the convex group, and now coming back to my theorem with Jeff, we can look at the fixed point lattice, so the cyclic subgroup generated by the G, and so what we take is we take the orthogonal complement and the corresponding vertex algebra, and then we take on this the co-invariant lattice Gx, we can take a list of it, and we take a fixed point vertex algebra, and now this will be our W, and then what it means is, we should explain then the correspondence partially, is that the fixed point vertex operator algebras W are vertex operator algebras with a modular tensor category isomorphic to the modular tensor category for the quadratic space with the quadratic form the negative of the one for the discriminant space of the orbit matrix. And we also have in this, we only know in certain cases, that the induced subgroup of automorphisms acting on this module, that this group has to have the following property, so that we get a perfect one-to-one correspondence between Shelton's VOA and this Niemeyer picture, that whenever K is an orbit lattice with given discriminant space, there is only one orbit under the double covert action of the orthogonal group of the lattice and the automorphic group of the VOA on the this R should be here. For all the 11 general results, the two general is D and J. Now, let me finish with some remarks. This conjecture is true for at least 4 of the 11 cases. So the 1 to the 24 cases is the Niemeyer lattice vertex algebra cases, it's not 2. Now, essentially this 1 to the A, 2 to the A case, the vertex operator algebra W is you take the EA root lattice scaled by a square root of 2 and then the fixed point, and this was investigated by Bob, and he showed that the automorphism group and also the induced automorphism group was followed, that this is the whole orthogonal group of the finite quadratic space, and therefore if in the double covert action you get only one class for each lattice. Now for the next one, order 3 element, what we have to take is you have to take the Coxeter top lattice under an element of fixed point and an element of order 3. And this was done by Shen, Lam, and Shimakura. And so this was 2. And the fourth case is by Scheitauer and myself, when we worked already partially out the action of the automorphism group on the class. Now, the uniqueness of this vertex algebra W, which you would need for the uniqueness of each of the Shelton cases, this one can also be used under certain general assumptions on the VOA by using the uniqueness of the Lichlet VOA. Now, I should say the reason for this Shelton's Niemeyer correspondence is only partially clear to me. So what I understand is how you can go from the Niemeyer picture with this cyclic subgroups to a Wellspool VOA, but why you get all of them, I have not the slightest idea why this is a case. And so you see that uniqueness conjecture of Shelton's requires that the automorphism group of this W has enough elements. And so the 71 is related to the existence of enough automorphisms, and with the Ox observation requires that the automorphism of the Bullsheim object has enough elements. In this sense, both 71s fall down to the same reason. Yeah, I should say that the last stuff I explained, you can find in my treatment, which should be up on the array in a few days. Yeah, so let me conclude that since its discovery in 1973, the monster was good for many surprises. It is the most unique known object in mathematics and probably also in physics and the universe, and several mysteries are now understood, but many old and new remain. The coming years will remain exciting, and I'm sure that the year number 71 will not be the end for to publish about the monster.
Questions? Comments? When you say quick grant in 2016, is it posted quick grant or?
No, I will in a few days.
Oh, it will.
Yeah.
And the blue code, is there a reference to that?
Yeah, I mean Bancroft is maybe better, but it's in the atlas. So the blue code, so you just have to look at the atlas for all the things in Niemeyer. There is a blue code together with the automorphism. So you just need to scale in the atlas and look long enough at it, and you can work it out.
The definition of a glue code, is comments on other comments?
No, for vertex algebra there is not a math formula known, but of course you can use a math formula check for each of the 11 genera. So I removed it because it didn't fit on the slide, but you can compute the, because in NAGMA I have the order of the automorphism, so it adds up, but I didn't really do the check because I know that NAGMA is doing it correctly, and to compute the mass constant is always hard. But for vertex algebra, it's no mass formula check, so that we don't know. So at the moment, we only have, so for the Shelton's list, we had this approach of Shelton's, which was the analog of Bancroft's for lattices, but it wasn't able, we cannot describe the generalized glucose which you need for BOH, because this is something in modular tensor categories which we don't understand so much. But what we can do is somehow we can use Niemeyer's original idea to using neighbors, which in vertex algebra generalizes to orbifold construction. So that's the actual way how constructed. But so my approach here is more or less more like this mass formula approach by Conway and Sloan for the numeric lattice. And in the paper I also have a 26-dimensional Lorentzian picture, which I didn't talk here about.
Okay, maybe we should, thank you.